Firstly, I must just clarify that my title's supposed to come up there. The science and the impacts of climate change and the effects on the natural environment, agriculture and water. And though I will be talking quite generally about Africa, I'll be mostly focusing on Southern Africa. And that's really just because of time. But of course, I will be available privately or afterwards and talk about some of the impacts in Africa, because I am specifically working also in East Africa. So for those of us who've been working with climate change for 10 or 20 years, as I have, we assume that everyone understands what it's about, what causes it, and how we know that it's real. But we really have to go back to the basics. And I'm sorry, Samantha said this wasn't an academic lecture, but it is going to be a little bit of an academic lecture, because I want you guys to be able to walk away with some ammunition, if you like, and resources, so that you know that climate change is a real issue, and it's not made up, and it's not a scare story. And if you've got climate skeptic friends, I'm afraid to tell you to tell them that all those skepticism can actually be debunked by science, and it's fairly sewn up. We're quite confident. So it's not a false alarm. It is real. We've seen here are some selected significant climate anomalies and events, which means these things are different to normal. These things stand out, and these things indicate that things are not as they used to be. Now, we've always had extreme events throughout sort of human history, but these are becoming more and more frequent, and you can see there isn't a place in the world that isn't being affected. And these effects are not temporary. If you look at that list on that slide, if you can see them, it's not a one-off. This is a general trend that we're seeing. Ice extent is reducing, rainfall is changing, temperatures are getting high, tropical cyclone frequencies are increasing. So something is going on. And the global temperature in July, which was summer in the Northern Hemisphere, was the highest for July since global records began in 1880. So that's, 140 years, we've now got the highest temperature. And every subsequent year is up in that high temperature range. And I'll show you some of the data in a minute. But let's get some facts here. And it's very clear that we must understand the difference between facts and fake. And as you know, there's a whole lot of false information and disinformation around, especially in the time of COVID. So we really have to separate the facts from the fakes. And it's not that we are stupid, and it's not that we don't understand. It's just sometimes we overlook the facts. Now, this is a map of Southern Africa, or South Africa, really, the country. And it shows you the broad rainfall regions, just in case we weren't completely sure, because we had a lot of rainfall in Durban, and people say that's unseasonal. It's April. Well, Durban is in a region that gets rain throughout the year. Not the same amounts throughout the year, but you can expect rain in any month of the year. And that region goes all the way down to George. Then you get the summer rainfall region, which is the bulk of the country. And then you get the winter rainfall region. And then two very dry regions, which actually the blue region gets rainfall, if it does get rainfall in winter, and the gray region gets rainfall in summer and winter. But it's so little, it's less than 100 millimeters a year, which makes agriculture and so on very, very unlikely there. So that's one fact. The second fact is that South Africa, because it's mostly a summer rainfall region, the graphs of the rainfall and the temperature look like this. Now, this is just a place in the center of in fact, I think it is Gauteng. It used to be called Warmbad. The name has changed now. But there you can see the rainfall in blue, and you can see the bulk of the rainfall falls between October and March. So it's a summer rainfall region, and very, very little falls between May and September. And if you look at it, 26 millimeters or 28 millimeters, sometimes in June 4 millimeters, July 1 millimeter, August 3 millimeters. So if it doesn't rain in June, July and August at all, we can't say that we have a drought. That's the normal situation. So we must understand that there's a normal situation which we call the climate, and it's the average weather. Now, in South Africa, the average rainfall is around about 620 millimeters. Now, many places have more rainfall, and many places have less rainfall. But that's more or less the average, and that's something we need to understand. Of course, the winter rainfall region looks different, and so does the all-round rainfall looks different, but I won't touch on that right now. This is an image to show you the situation during one of the seasons. It's a satellite image, and it's called a false color, but it indicates the vegetation during a specific season. Now, I would ask you normally, if this is a classroom situation, to suggest which season this is, but I can't do that. But I'm going to ask you to try and answer in your own minds which season is. Is it summer or winter? I'll just really, rainfall season is immaterial because you've got summer and winter rainfall. But do you think this is a summer situation or a winter situation? And if you said winter situation, then you were confused, because the winter situation means that the interior is dry. And clearly from the green, we can see that there's vegetation in the interior, especially the eastern interior, the summer rainfall region. And that green indicates that there's been rain. And so that would normally show a summer rainfall region. And then you'd go down to the Western Cape and say, okay, if it's summer, then there should be dry areas down there. And indeed there are. Now, I can't remember how to put the pointer on. There we go. So if you look over there, you'll see a dry region. And hopefully if we go to the winter picture, you see something which corresponds to dryness in the interior and greenness over there. Now, this is the state. This is the fact. This is what it looks like. And if we're talking about climate change, it's a situation where this may change. And we're not exactly sure how it will change, but we're going to investigate some of those possibilities. We know what causes these conditions because we understand the system. So in summer, we have a low pressure in the interior, and low pressure, if you go back to your geography lessons at school, low pressure indicates unstable conditions. Air is rising, moisture is condensing, and generally speaking, you see moisture or rainfall around a low pressure cell. A high pressure, the air is sinking, it's descending, stable air, it doesn't have a lot of moisture in it, and you'll see fine weather here. Now, the direction of the rotation of the winds is also important, and around a high pressure, the wind goes in an anti-clockwise direction, and we get easterlies along the coast, and here it goes in the clockwise direction, so we will also get easterlies because it's going around like that. So you can see an easterly circulation bringing rain to the interior and fine weather to the Western Cape, and that's in summer. That's the situation, and these cells are situated like that, bringing our conditions. Now below, you'll see these systems over here, which are called mid-latitude cyclones, which would bring rainfall to whatever's in their path. So there's an island over there, and it's got a full cloud cover, and it's raining because it's in the path of these mid-latitude systems. And what happens in winter is that the systems shift because of the tilt of the earth and the seasonal shift, and these systems move. So that low pressure has moved further north, these low pressures moved further north, and this high pressure are now dominating the situation here. And the high pressure, remember, is dry and stable, so we're seeing dry and stable conditions over the interior. No rainfall. Just a reminder, this is August, so it's winter, but now the cold fronts are coming past the Western Cape and bringing rain to the Western Cape. Now, without these cold fronts, there would be no rain in the Western Cape, absolutely none. And you will have remembered in 2015, 16, and 17 that we had very few of those cold fronts, and then we had a very, very serious drought. So that's the only thing that brings rainfall to the Western Cape. So if something happens to these cold fronts, then the Western Cape is in serious trouble. Whereas if we look at the previous situation in the interior, this low pressure is vast, it's huge. And although we do get intermittent droughts, the chances of a 3 to 4 year drought are very, very small, tiny in fact, because this low pressure system is a much bigger system than this little frontal system, which only passes, really just scrapes past us 100 kilometers, 200 kilometers in width. Okay, so here's a quick question for you. You may or may not have been to these cities or recognize these cities, but these are three major cities in the world. Let's see, we can see this is Cape Town, but I'm talking about an average South African city here, and this is, if you don't recognize it now, it's because those buildings aren't there, but that's the Empire State Building, so immediately you know it's New York. And this one you may know because there's an iconic telephone booth and a red bus, and the Big Ben Tower, Houses of Parliament. So this is London, this is New York, and this is the average South African city. Which one of those cities has the highest rainfall? Now, I can't hear you shouting out, but I think you probably are calling out. In my experience, you're probably saying, well, London is always wet. We know that. You can see in this picture, water's lying around. And then we don't really know about New York, but remember seeing movies that, there is rain in New York. So maybe this one is the most, this one's the second most. And because South Africa is a dry country, maybe that 620 millimeters I was talking about for South Africa is the lowest. But you see, this is where we get our facts wrong. New York gets 1,260 millimeters a year. South African cities get between 620 and 830 millimeters a year. So as I said, around about 650. And what about London? Oh, that's a surprise. That is really a surprise. And usually when I'm giving this talk or presenting these facts to people, they immediately haul out their phones and they Google London's rainfall. And if you did that, you would get, sorry, I skipped that slide, but if you do that, you would get exactly that, 583 millimeters of rainfalls in London. So one then asks ourselves a question, why is South Africa so vulnerable to droughts? Why is South Africa such a vulnerable, or got a water scarcity problem when it's got more rainfall than a city like London? And the answer is because the rain doesn't always fall at the right time. In the summer rainfall region, the rain falls in summer, which you'd think is good for the crops, but because it's very, very hot, that water evaporates. If you come to the Western Cape, we have crops that need some rain in winter, but we also have fruit, and that fruit needs water in summer. So you have to collect the water in winter and make sure it's available in summer. And if it gets hot, that water evaporates. So it's really the heat that's exposed in southern Africa as opposed to areas like London that make us more susceptible or vulnerable. Now, you might think, what has this got to do with climate change? And I'm coming to that. So, what is this deal with global warming and climate change? Those two terms are used interchangeably, but we must understand that the thing that we're really concerned about is global warming. Global warming is the heating up of the planet to a degree which we haven't seen in millions of years. Now, you might say, oh, we don't know, we weren't around, so I'm going to unpack that a little. But it's the global warming that we're measuring that is leading to climate change. And the climate change that we're facing is much more sudden and fast acting than the climate change we've seen in the past. So some quick questions your mother might ask you, or your father, or your girlfriend, or your son, or whoever might say to you, is it real? How do we know? Is it already started? What's going to happen? Can we stop it? And then what about things like food and water and even the natural environment, for animals, not just for humans? What's the situation with that? And we're hopefully going to be answering those questions today. So what's the deal with carbon dioxide? Why is carbon dioxide such a big deal? If you did biology at school, and remember, I'm assuming you all went to school, I've already mentioned geography, so I'm assuming that you did a couple of these subjects, and if you did biology or life sciences, you would understand that there's a carbon cycle. The whole world, in fact, rotates around carbon, because without carbon life forms, none of us would be here. There'd be no vegetation, there'd be no food, we wouldn't exist. We may exist in another form, but on our planet, carbon is very, very important. And there's a cycle of carbon, and it cycles around the atmosphere. But if you look very carefully at this map or this picture, you'll see that there are only a couple of arrows that don't go both ways. And you can see there's an exchange going both ways. There's photosynthesis and respiration going both ways, ocean circulation, etc. There's one that says land use changes are resulting in increased carbon going into the atmosphere. Fossil fuel combustion, increased carbon going into the atmosphere. Now, why is carbon so important, or why is it so useful? Well, generally speaking, we're all carbon life forms, and every time we breathe, which you've probably done about 4,000 times since I started this talk, your body, which consists of carbon, which is essentially the food that you ate this morning or during the day, reacting with oxygen to form heat. And that heat is essentially the energy that builds up the cells in your body and restores your body. It's energy. It's another form of energy. And if you put your hand to your throat right now and you touch yourself, hopefully you're hot. If anybody isn't hot, please alert the person next to you, because we might have to rush you to the hospital. But that's what happens. And the byproduct is carbon dioxide. And this carbon dioxide is released into the atmosphere. Now, it's perfectly normal. This is the way it works. And that carbon dioxide normally gets reabsorbed, and there's a balance of what happens. Now, the greenhouse effect is now something that takes advantage of this carbon dioxide. The greenhouse effect is, most people think, a terrible thing. It's really, really bad thing, but actually it's not. What it is the effect of the atmosphere around the planet, which contains certain gases, which absorb the sunlight that is released or given off by the Earth. The sunlight comes through the atmosphere, mostly, hits the Earth, is warmed up, and then the warmth is re-radiated into the atmosphere. Most escapes to outer space and cools the Earth down, otherwise we just get hotter and hotter and hotter. But some is trapped by the gases in the air and reduces the cooling. So at night time, when the sun is out, when the sun is gone, we don't get as cold as the moon does, for example, which is the same distance from the sun, works the same way, it rotates and gets sunlight on it. But the moon gets to minus 36 degrees Celsius at night. Now that is super cold and we wouldn't survive. So the one reason, and that's why we call the Goldilocks planet, not too cold and not too hot, the one reason we can survive is because the atmosphere is absorbing this heat and keeping us warm within the range of our bodily functions. So everyone knows that a comfortable temperature, really, if you've got enough clothes, is between about 10 degrees and 35 degrees. Outside those ranges, you actually get very uncomfortable. So we've got a very small range that we're suited to, and that's one of the issues that we have to worry about. So that greenhouse effect is good, and the carbon dioxide and some other gases are absorbing that heat within the atmosphere. All good and well. And the key greenhouse gases are carbon dioxide, methane, nitrous oxide, and then some fluorocarbons. Now these are not natural processes. The nitrous oxides and the CFCs are from manufacturing and combustion of solid waste and fossil fuels. Carbon dioxide is kind of a natural because there are always fires around and people have been burning wood, which is made of carbon and it's carbon neutral, if you like. But then methane is a very powerful gas. Now when I say powerful, I mean the greenhouse warming potential. And if carbon dioxide is set at 1, methane is 21 times larger, and then the other gases are even larger. But there are very few of these gases by concentration. Carbon dioxide also, not much of the atmosphere is carbon dioxide, 0.025%. So it's a very small amount, but it is the predominant gas which absorbs that heat. The other gases don't, and the other gases, as you remember from your geography and lessons, are nitrogen and oxygen. Those are the two predominant gases in the atmosphere, nitrogen 79 and oxygen 20. And all the other gases make up the other 1%. And carbon dioxide is the most prevalent of those other gases. So that's the deal. These are the greenhouse gases within the atmosphere. The other ones don't really bother us. Now, increased carbon dioxide and methane levels are increasing the greenhouse effect. So more heat is being absorbed by the atmosphere due to the increased level of these gases. So where do these come from? Well, we know that there are three main causes. One is electricity generation, because still for the last 150 years, we've been generating electricity by burning coal and oil. And these are carbon forms that have been laid down under the earth for thousands, if not millions of years. And we are releasing that carbon in a very short time. And that means that the carbon dioxide concentration in the atmosphere is increasing very, very sharply. Transport also uses fossil fuels. That's it's almost equal to electricity generation if you think of how many cars there are around the planet. And even electric cars often use electricity that is produced by fossil fuels. So they're not really not to blame. They're also to blame. And the third one is agriculture. And agriculture might seem a very strange one, because where does the carbon dioxide come from agriculture? Plants absorb and release at the same time. There's a balance there. And the answer is quite complicated. Firstly, the number of cattle that we have is not proportional to the surface area that has always been sustainable. So we've got far more cattle than we've really ever had. And it's not the carbon dioxide that the cattle produce, it's the methane. Cattle breathe out methane when they chew the cud, and this is due to the fermentation in their stomachs. And that methane, as we said before, is much more powerful as a greenhouse gas, warmer than carbon dioxide. So there, the prevalence of cattle, because we all eat a lot more meat than our forefathers did, the prevalence of cattle has increased the amount of methane and therefore the amount of greenhouse gases. By clearing the lands and the forests, inadvertently, what we are doing is replacing them with crops. Now, crops are also plants, so they also absorb carbon dioxide, but they only do it for about 3 months a year, because that's when the crop's growing season is. And for the rest of the year, the land stands fallow or has very little vegetation on it. So what you've done is you've replaced vegetation that is absorbing carbon dioxide 365 days a year with something that's only absorbing carbon dioxide for fewer than 100 days a year. And the net result is that more carbon dioxide is therefore staying in the atmosphere. So the bottom line is more greenhouse gases leading to more heat. The question, haven't the temperatures of the Earth always been changing? And that's absolutely true. If we go and we look at some graphs in a minute, the temperatures of the Earth have been changing. There's historical changes that have happened for various reasons. Is that due to greenhouse gases? And that is absolutely not, because nothing has managed to change the concentration of greenhouse gases except the actual change in the Earth's temperature. And it's been a different kind of relationship. And I'll talk about that in a minute. So what we can explain it with is a thing called Milankovitch cycles. And this has to do with the sun. And the sun, over the years, changes in its distance from the Earth. So when the sun is slightly closer, then we get slightly warmer. If the sun gets further away, we get slightly cooler. And there are three things here, and you can go and research them later. Milankovitch put it all together as a theory. And they've got different periods of return. There's eccentricity, there's precession, and there's tilt. And these things all vary over thousands of years to bring us closer and further away from the sun. And these are perfectly natural, and they're part of the cycle of the planet. So we expect to see them in the record. And this is the record of ice cores in the Antarctic that show us the amount of carbon dioxide in the atmosphere, the amount of methane in the atmosphere, and the temperature of the atmosphere. And these go back, and you must look very carefully here, because this is 400,000 years ago, and this is the present. So it goes from a long time ago, almost 500,000 years ago, to the present. And this is the amount of ice that has been laid down in the Antarctic during a very stable period of the Earth when there was very little tectonic shift, and the continents were all in place, and the climate was very much stable because there weren't a lot of volcanic eruptions or asteroids or anything like that. And if we look at this and we look at the temperature, and the temperature is registered or is measured by the size of the particles of gas inside the ice. And there's a very, very complicated technique, but we can analyze the temperature or extract the temperatures at the time relative to today's, and also the concentration of gases that were present in the atmosphere at that time. And no one disagrees with this. This is well-known science, and it's used a lot. And this is the record, or the Antarctic time series, for about 500,000 years. So what do we see? We see that the temperature went down over hundreds of thousands of years. This is 100,000 years from there to there. So it's 10,000 years there. It goes down, 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 then reaches a minimum, then suddenly goes up again, down, 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 a minimum, up again, down, a bit erratically here, but down to another minimum, up again, down again, and up again. So we get these cycles related to the Milankovitch cycles, which show us periods of warming and periods of cooling. And in fact, the periods of cooling are far longer than the periods of warming. And that we don't completely understand, but that's when the Milankovitch cycles came to an area where the Earth was now very, very much closer to the sun than in other periods. And you can see now we are sitting in an extended period of warming, which in fact has made our lives very comfortable. And I'll talk about that again a little more. But what about the other gases? We see there's a direct relationship between the concentration of gases and the temperature. When the temperature is high, the concentration of carbon dioxide and methane is high. And the reason for that is that when the temperature is warm, the ice, the permafrost, which contains a lot of methane in very cold climates like northern Asia, that ice melts and releases methane into the atmosphere. The oceans can also hold much less carbon dioxide when it's warmer. And this is a bit like comparing a cold Coke to a warm Coke. A cold Coke is very, very fizzy. A warm Coke is not very fizzy. So the warmer the ocean, the less carbon dioxide it can dissolve, and the more will go into the atmosphere. So what we've got is the temperature of the Earth causing high levels of carbon dioxide in the atmosphere. Now that would also presumably have a feedback and cause the temperature to increase as well. And that's also not very well understood because we don't really have detailed records of that, but we can see that there's a relationship. What we do know is there were not people on the planet increasing that temperature or increasing those carbon dioxide levels. This is the natural sequence. So from this graph, we deduce that there's a very strong relationship between the temperature of the Earth and the concentration of gases in the atmosphere. Now let's have a look at this present period now and see what's going on here. First of all, over the last 800,000 years, these are the carbon dioxide levels in the atmosphere. And right now, we are way out of the range that was happening there. The range there was between 180 and maximum 300 parts per million, and we're now sitting at 420 parts per million. So that's very important. This was in 2019, 415, and we're now sitting at higher than that. But let's look at the last 1,000 years, and we'll see that the temperature has actually remained very constant. You'll see that there's been a decrease in average over the last 800 years of about 0.2 degrees. But since about 1900, the temperature has changed direction and in fact really increased compared to the increases we've got here. Now the orange, the yellow or the green color, whichever color you can see, is the margin of error around these measurements. And you might ask again, well, how do we know these measurements 1,000 years ago, 1,200 years ago? Well, they've been reconstructed from things like tree rings, from written reports, from deposits in lakes and rivers, that we can determine what the temperature was like at a certain time because of the amount of ice that melted or because of the germination of certain seeds and so on. It's also not disputed. There you will see a variation, and this is in the 1960s. There was a cooler period, and there's still evidence of an increase. And now we're going to look more closely at this period and ask ourselves why. So these are the last 150 years, and this is the change of temperatures. And if we look at the rate of change, you've all done maths and you'll understand what that means. It's the change over time, and that was the 100-year rate of change, and this is the 50-year rate of change. And you can see that the change is getting greater. The further we go into the future, the more this temperature seems to be changing, and it's in what we call almost an uncontrollable increase now. We just don't see any sign of the temperature increasing. And what we've done here is we've extracted the El Nino years, which were very hot compared to other years. And I'm not going to talk about El Nino now, but it's a warming of the Pacific Ocean, and you can read about it. And 2018, 19, 20, and 21 have all been up in this area. So there's no evidence of us going down. And some would have said, if we go back to this slide, some would have said, but surely we are due for another ice age at some point. And we suspect we are. When that Milankovitch cycle kicks in, we suspect we are. But it may be that we've increased the carbon dioxide level so much that that cooling might not happen. That's not going to affect us because that happens over tens of thousands of years. And I'm not so sure if we've got a sustainable planet that will last us that long. The warmest 7 years have all occurred since 2014. Okay, so this is something that's happening. We've seen the carbon dioxide levels. We know why this is happening. But what is it during the last 150 years that's introduced so much more carbon dioxide into the atmosphere? And the answer is obviously the Industrial Revolution, where oil and coal have been mined at rates that were never mined before. We've been extracting hundreds of thousands of barrels of oil out of the ocean, out of the soil and the oceans, and also tons and tons of coal, and burning that at rates that have never happened before. And that's the only reason that we can explain this increase in temperature. But still, people will say, but hang on a second, are you sure it's not a natural cycle? Are you sure that this isn't just the way it is and everything's going to be okay? And it's a fair enough question. So what did we do? We turned to the science and we did some modeling, and we approached the modelers and we said, okay, we understand the processes in the atmosphere. It's all physics. What we want to do is we want you to pretend you're in 1900 and predict what the climate is going to be like by 2000 if there were no human-produced greenhouse gases. In other words, it was a natural planet without anybody on it producing greenhouse gases. And this is what they said would happen. They ran a bunch of different models. Naught is the baseline temperature in 1900, and they saw that the temperature would naturally increase, decrease, increase, decrease, increase, decrease, increase. But after 100 years, it would more or less be the same as it was. And the average changes very, very little, by 0.2 degrees maybe. And what we've actually seen is this black graph. So it doesn't explain this difference. This is the natural cycle, and this is the actual cycle. So what do you do then? You then go back to the scientists and you say, okay, right, guys, as you were, now you can do the modeling with humans on the planet producing, and we know how much coal has been burnt, we know how much oil has been used. You do the maths and work it out, and that's what their graph looked like. So as far as we're concerned, as climate scientists, we are not open to debate anymore. There is no debate. The science is there. It's been peer reviewed. We know two things. One is that the temperature has been increasing. There's absolutely no doubt about that. And secondly, we are 99% sure that it's due to human-produced greenhouse gases. Now, there's always a 1% because we cannot claim to be infallible. We cannot claim that we know everything. And certainly science is all about change. And eventually, many theories are changed or adapted, and some are even overthrown. But we're pretty sure from 25 years of research that this climate change thing is real. Okay, so I've taken a long time to give you some of the basics, and if you want to read up on about it, this is the sixth climate change report from the IPCC. It was just released in December last year, and there have been two subsequent volumes that have been released. This is the physical science, which is I've been talking about, and then there have been impacts, mitigation, and the social aspects of climate change. And these have been coming out. This is the sixth series, but this is the problem. The first one came out in 1990, and the scientists stood up and said this is going to be a problem. In 1995, definitely a problem. 2001, guys, can we sort this out? 2007, and now this is around about the time some of you were born, and still in 2021, very little has changed. And there aren't many agreements that are binding on nations. And vast countries like the United States are using more greenhouse or producing more greenhouse gases than ever before. And this is the problem. And we're going to have to deal with this problem. These are some of the facts that have come out over the last 3 or 4 years of increasing temperatures. Now, if you look at the numbers there, you'll wonder how people can survive. 51 degrees, 49 degrees, 48 degrees. And the answer is that if these temperatures are sustained, people cannot survive. They will die. Animals will die, plants will die. These are massive increases. And this is a worry. So your answer is, well, go to a cooler place. Okay, well, you tell those people. But look at these places. This is Canada. Okay, this is Sicily. These are not the deserts. These are not places that are typically very, very high. These are places that have got fairly high populations. So this is a problem. What are the forecasts for Africa? What are the IPC or what are the scientists saying for Africa? Now, this is quite complicated, but there are certainly projections that are saying that there's a 1.5 degree global warming increase, and you can see that that is in northern and southern Africa, that there are possibilities of a 2 degree global warming increase and a 4 degree global warming increase, depending on how we respond over the next 80 years. So this is all by 2100. These are the projections for 2100. The precipitation is different. Some of the places are getting wetter. Certainly in the northern hemisphere, we're seeing places getting wetter, but everywhere and almost all the projections, and we're looking at total precipitation, are showing a dryness for southern Africa, and that goes almost all the way up to the equator. The maximum daily precipitation, in other words, the intensity of the rain, is increasing. Maybe in the Western Cape it's decreasing, and this is a worry. So it's quite a complicated thing when we get to rainfall, and I'll show you that also in a minute. So temperatures for southern Africa over the short term, we're looking at about a 1.8 to 2 degrees warming, and less near the coast and more in the interior. This is December, January, February, and June, July, August, which is summer and winter respectively. This means that not only is the average temperature increasing, but also the number of very hot days is increasing. So days where temperature over 40 are increasing, days with temperature over 30 are increasing, and nights are not getting as cool as they used to be. Now that might be nice, you say, that you don't get less frost, and well, we're not necessarily seeing less frost, but we're seeing less cool nights, and fewer cool nights mean warmer next days. So that's an issue, and many crops and many diseases are controlled by those cool night temperatures. So that may or may not be a problem for specific activities. Let's take a place like Bothaville. Now I took Bothaville because it's the center of the maize region in South Africa. And this is quite important for growing maize because maize is a summer crop. Now, this graph shows you, the gray bars show you the number of days over 32 currently observed. Okay, so you'll see in January there are about 10.5 to 11 very hot days over 32 in the historical record. The red shows the number that this is going to increase by, and that increases by about 6.5 to 11 more days over 32. Now, maize does not like temperatures of 32. It can take it 1 or 2 days in a row, but it doesn't like a lot of them. So if you're going to get 21 days in January with the temperatures over 32, this may very well be a problem for growing maize. And you'll see that this persists right through the drying season or the growing season of the maize. Another almost 8, between 6 and 10 days over 32 in March. And we see similar things in the early summer. In the winter, we're seeing an increase of those hot days, definitely in all of the months, but then the crop's not really growing. But it does mean that the soil moisture is being affected. So that's one of the important impacts on crops, but also on natural vegetation. And I'll talk about some of the impacts of that too. So what are the threats of temperature? Very high temperatures, prolonged heat waves, more evaporation, decreases in soil moisture, drying out occurs more often, increased transpiration, alien vegetation, and fire. Now, alien vegetation is a predator, or it's a pioneer plant very often, and they enjoy these extreme temperatures, and very often they enjoy the low rainfall because they've got very deep roots, and so they seem to thrive in these extreme conditions because that's just the very nature of them. They're pioneers. They go out and they can withstand a little bit of suffering, as opposed to the vegetation that has evolved in the area. Fire threat, obviously, with increased temperature. Now, this all results in more vegetation damage, whether it's crops or natural. So this is something that we must be concerned about. Increasing drought has been identified at certain parts of the world, mostly the Mediterranean regions, and you can see Southern Africa is definitely being identified as a place which is going to get more droughts, okay, as the earth warms up. And another scary one is to see the Amazon Basin as well get drier, because that's a major source of moisture that brings us and other places in the planet rain. So just to give you an indication, you know that we've been in a drought, especially in the Eastern Cape, and some of the places maybe the drought may have broken. But this indicates a 3-year drought, which is a long drought. And you can see there are large areas of the country that have suffered a 3-year drought. And if this is getting worse and worse, that is going to be a problem. And this is the impact on the vegetation. And you can see that this orange is very much below normal situation. Yes, this was winter, and this was 8 or 9 months ago, but it's still much lower than normal. So you can see vast areas of the country suffering from less vegetation than is normal. And this is all very complicated, but essentially this drying, models have shown that it's going to have a very, very severe impact on food production. And this is one of the sort of scenarios that we've run to show you what might happen in the future. Now, I haven't shown you many of the scenarios here in this slideshow. They're quite complicated, but we have to ask ourselves where we're going to go to in the future. And that first slide shows you a little bit about the options. If we continue as normal, we are looking at a 3 to 4 degree increase by the end of the century. And if we do something about it now, and have to be pretty drastic, we're only looking at a 2 to 3 increase. But we need to keep it below 1.5 in order for our systems to be stable. And that just doesn't look like it's going to happen. I'm going to skip over these slides now because I've discussed them in some detail and I'm seeing I'm running out of time. But let's look at rainfall projections for Southern Africa. Now, it's very, very difficult to predict rainfall because you know that you can live in one place and get 20 millimeters rainfall in a day, and then just 20 kilometers away, someone will phone you up and say, oh, we haven't had any rain. So how can we predict what's going to happen in a specific area? And it's complicated because models don't really understand how the rain falls. They can see the clouds forming, they can see the temperature decreasing, but they cannot actually see how much dust is in the atmosphere to form the condensation nuclei and how much rain is actually going to fall to the ground. So they create scenarios, and we have wet scenarios, dry scenarios, and average scenarios for each season. So that would be summer. March, April, May would be autumn. that would be winter, and that would be spring. So if you look at the wet scenarios, you can see that there are small increases. And I've just picked an area in central South Africa where the rainfall may go up by 20 millimeters in those 3 months. Now, those are the rainfall months, so you'd think that was good, unless the rainfall is more intense, which is a problem. March, April, May, a similar situation, up to 15 millimeters. June, July, August, which is winter anyway, maybe 5 millimeters more, and then maybe 15 millimeters in spring. Now, that's the wet scenario. If you go to the dry scenario, whoa, 10 millimeters less per month, 20 millimeters less per month, 5 during midwinter, which is hardly any, and then 5 millimeters less per month again in the springtime. And the average of the models is showing that for virtually the whole country in the summer rainfall region, there's a very, very small increase in rainfall. So we don't know which way it's going to go, but what we are suggesting is that it's going to be highly variable. What we do know, though, is that the rainfall is likely to come in more extreme events because the whole atmosphere is more excited. There's more energy in the atmosphere. It's hot, it's cooking, and it's very much more energetic. So we're expecting more extreme rainfall. What we saw in KZN last week was a unique event of two systems that were on top of each other. One was a cutoff low and one was a coastal low, and they just happened to be there at the same time, and they combined and they formed tremendous uplift and tremendous rainfall. Now, we're not saying that's going to happen more and more often, but we are saying that situations and extreme events like that are more likely to happen more often. So what we see here is a little bit of increased rainfall, but with increased temperature, this increased rainfall is not going to make much difference at all, unless it's about the intensity. So the general picture is the eastern part of the country is likely to get a little bit wetter. The northern part of the country is certainly hotter and drier, and the eastern half of the country also, the western half of the country, hotter and drier. That's the sort of general outlook that we've got. What's important to understand is that you have got, within a certain climate, you have got activities that actually situated in this box, which is a coping range. So you can cope with increased temperatures and decreased temperatures because whatever activity you're doing, whatever plants are growing, whichever animals are surviving, and whichever agricultural activity you're doing can survive. When these temperatures start to escape out of this box, you get into a very vulnerable area, which is the orange. Unless you can cope with that by increasing your coping capacity through adaptation to this increased temperature, your activities then become very, very vulnerable. And it's this coping strategy that we really have to focus on. And I'll be talking a little bit about that. So what can we do? We have to ask ourselves, what are the risks of higher temperature? What are the timing of ecological cycles, our crop maturity harvesting? What are the risks of a reduced temperature range? In other words, the minimum temperatures are not going down as much, so the difference between the minimum and the maximum is narrowing. What's the impact on fertilizer, pesticide, and herbicide application and their introduction into the natural environment? Farmers are using more and more pesticides and fertilizers to deal with the situations they're facing because pests are breaking out more often and they're being subjected to these extremes. Will increased irrigation requirements be sustainable? We know we don't have enough water already, so how are we going to deal with increased irrigation requirements? And what's going to happen to the crop and vegetation quality? We've seen some fertilization due to carbon dioxide levels increasing, so some plants are actually growing more vigorously, but we've seen reduction in the quality of especially things like fruit, where we get bigger apples, bigger pears, but the quality of that fruit is not as high. The sugar levels are not as high, and they're not as tasty. And then we've also got the issue of dealing with different pests and breeding cycles. We've seen things like the false codling moth, that breeding cycles are increasing 3 times. So if they had 2 breeding cycles here, they now have 6 breeding cycles here. And this makes it more difficult and more expensive for farmers, for example. We also know that different sectors use different amounts of water, and we also know that agriculture is one of the sectors that's going to have to grow in order to be able to feed our population. So we need to be aware of this, and we also need to be aware that there's a looming water crisis for various reasons. Agriculture needs water, people need sanitation in their houses, we have a low and unpredictable supply, there's a high demand, there's poor use and management of our water resources. These are facts we have to face. So a looming water crisis is something that's going to happen. You heard about day zero in the Western Cape, but it was postponed to, we're not sure. And funnily enough, this winter is not looking all that great. We've got enough water right now in the Western Cape, but we have had very, very low rainfall. April has been one of the lowest rainfall years in a long time, and we're not seeing any rain for the next week or so. So we're getting a little bit worried. Fire is a huge issue. Can you imagine? Less water, the vegetation is drier and the temperatures are increasing. Global wildfire danger is increasing across the globe. You can see those graphs just going up and up and up. That's 30 years worth of data. Persistent fire weather season length is increasing in the Mediterranean regions. And these are often the places of natural beauty, for example, the fynbos in the Western Cape. In California in 2021, a journalist asked, do you think the average person is making the connection between the fires and climate change? And the expert said, sadly, they don't. Journalists hardly bothered to explain the logic, and it's hard for people to understand that an increased probability is not 100% certainty. We must see these connections, we must take them to heart. This is not something we need to see in South Africa. President Trump in 2019 said nobody would have ever thought this could happen. But the science community had been warning them year after year after year that it was very likely to happen and that they needed to do something about it. But politicians don't normally listen to scientists. Then there are other issues I'm just going to touch on very briefly. There's the idea of melting ice, and we must remember that a lot of the ice is tied up in the Arctic Ocean, and this isn't not going to affect sea level rise because this ice is actually floating. Now, floating ice, when it melts, doesn't change the level of the sea. And I want you to do this experiment. Take a couple of blocks of ice, put them in a glass, and fill the glass up completely with water till you can't fill it up anymore. So it's completely full and the ice is floating. When that ice melts, you can even put a tissue under the glass to test this. When that ice melts, see how much that water level rises, and you will see that it doesn't rise one bit because the level of water has already taken into account the volume of that ice cube, and that's physics, Archimedes' principle. You can go and look that up. So even if all this ice melts, it's not going to affect the sea level. Although if this ice melts, you're going to have to ask, well, if it's melting this ice, then it might melt some other ice which is on land, and if you add another ice block to the glass of water, into this, in other words, if you take this ice and add it into the ocean, and this is not floating ice, the sea level will rise. And this is the extent of the Arctic Ocean reduction over 20 years up to 2011. It's far smaller right now. This is an animation, that's why I left it in, but I took the animation out because we're running out of time. So to put this in words, Greenland Ice Sheet and the West Antarctic Ice Sheet are showing alarming signs of thinning. If either of these melt completely, there's enough ice to add to the sea to raise the sea level by 7 meters. A global temperature rise of 2 to 5 degrees might destabilize Greenland irreversibly. So these temperature rises lie within the range of future climate projections. Now, those of you in Botswana, those of you in the Free State, those of you in Gauteng, don't worry. But if you're living in PE, Kaberge, East London, Durban, Cape Town, Saldanha Bay, worry. Because 7 meters will wipe out many of the coastal cities around the world. And that's a huge concern. Such a concern that the Minister of Fisheries and Agriculture in the Maldives, an Indian Ocean island, had a cabinet meeting underwater to show the rest of the world that this is something that's going to happen to their island unless they do something about it. And needless to say, that's COP15, we've just had COP21, and nothing has changed. There's also something about the Atlantic thermohaline circulation, which is the ocean currents, massive ocean currents, which are going to be affected by the melting of the ice, and that can cause freezing up of northern hemisphere cities. It's probably unlikely to happen in our lifetimes, but it's something that could definitely threaten those extreme winters as the cold water from the ice sinks into the oceans around there and causes. We've had some storms like that in Russia and in North America already, caused by the ice melting and the water in those oceans becoming very, very cold, and that introducing vast cold air masses which bring severe winters. So is there any good news? Well, there is some good news, as we can make a difference. There are protocols for decreasing emissions. We are seeing alternative energy coming in. Even Mr. De Ruyter's today issued a statement saying that Eskom, we can reduce our load or our load shedding, for example, by switching to more natural ways of producing energy that don't also link to climate change. He's not making that link, but that link is there. Water consumption can be reduced. We've shown that in Cape Town. We waste far too much water. We can increase our coping capacity through planning. We need to get used to rapid readiness, which means being forewarned about things that can happen. And that, unfortunately, means looking at improving our infrastructure. We know that if our infrastructure had been improved, then the damage in KZN would have been far less. And what we're dealing now is response. And response is much more expensive than readiness. We need to realize that. And then lastly, and not lastly, this is the last point that I've got, sustainable and regenerative agriculture. Farming in line with what nature is expecting are becoming more and more popular, and there are more and more people doing that. So I've gone on for a long time now. We haven't had a power shutdown here, but I was asked to finish by 2 o'clock our time, and it's just about that now. So the bottom line is, what if this whole climate thing is a big hoax? We do all this for nothing. Now, clearly you can see that climate change is an important issue. But to solve the problem, we really have to do the things that we see in the SDGs anyway. We have to do the things which we respect nature, we respect clean air, we respect clean water, and we do the kind of things that we should be doing already. And that's going to help us to solve the climate problem. Thank you very, very much.
So let's get into the question and answer segment. Feel free to ask any questions to Dr. Johnston. You can use the chat function. Just type out your question. I'll be able to read it out to him. Or you can use the raise hand function at the bottom of your screen under reactions. Or you can just switch on your video and raise your hand, and I'll see you, and you'll have the floor to answer the question as well.
Dr. Johnston, I'm not sure if you really highlighted well the link between the frequency of fires and climate change. So you may want to touch on that. The pictures were really, vivid and emphasizing the point, but I'm not sure if you touched well the link between fire frequency and climate change, global warming.
Would you like me to answer the questions as they come up, or should we wait after a few? I'm happy to do it as they come up, then I don't lose track. Is that all right? Okay, great. So thank you for the question. And yes, if you've studied fires, and I know wildlife, there's a fire management component to any sort of wildlife studies. If I remember correctly, there are three important things about a fire. The first one is ignition, the second one is antecedent conditions, and the third one is the load. So these things have to be there before you have a fire, and it's the antecedent conditions and the ignition that really are affected by climate change. If you have a series of very, very hot days, not only does the vegetation dry out, but you increase the chances of ignition because of the high temperature. Spontaneous combustion can happen, and even if there is something like a lightning strike during a thunderstorm, after a very dry period, that can ignite the lands. But it's the sustained high temperatures that offer the highest risk to fires, and we've certainly seen more and more fires. And because the fires are burning hotter, they're spreading faster, and they're much more difficult to control. So that's the real thing behind fires, and there's definitely a very, very close relationship between increasing temperatures, changes of rainfall, and the frequency of fires.
Thank you.
Thank you. And thank you for your question, Dr. Richard. We also have a question from the University of the Free State.
My question is, if the water levels would rise, what would happen to those coastal ecosystems, like the ones on the sandy beaches and the rocky shores?
Yeah, another great question. Thank you. So what we've seen is that some of the shores have got natural resilience, especially the ones with mangroves, where they've been where they've been normally quite big tidal ranges. And tidal ranges have effectively created the beaches and changed the beaches, and we've had storm surges and things like that that have had an effect on the beaches. And one could say, well, they've damaged the beaches and they've damaged the ecosystem. But over the long period of time, that damage can either be permanent and it just changes the nature of the beach, or else it just is cyclical and the beach comes back again, especially if wind blows the sand, ocean currents blow the sand back again. The problem is when you have human interference and you create artificial things along that coastline. So if there's no human interference, then I think one has to accept that there will be natural variations already, and the increasing sea level, which we don't expect to be enormous. What we're talking about is a couple of centimeters per decade at the moment. Of course, that can increase drastically over the future. But because those changes are quite small, it's unlikely we're going to see everyday events. But storm surges and high tide, spring tides, could create more damage because the sea level is encroaching an extra 2, 3, 4, 5, maybe 10 meters up the coast. And we've seen damage to sea cliffs, we've seen damage to sand dunes through that. When it comes to human intervention, and we've seen houses right next to the ocean, there's been massive erosion of those houses, and we can see infiltration of water into their foundations and all sorts of issues with seawater infiltrating into freshwater systems. It's really something you'd have to ask an ecologist, because I'm not qualified to answer the specific questions on the natural vegetation and the natural impacts. But certainly, when the sea level rises and you have a storm surge and a spring tide, that water is much likely to go further inland than it used to be. And that's because the beaches are sloped very shallow. So a small increase in the sea level leads to a large increase in the surge.
Thank you for your question. We have another question from Andrew Mariti. I just want to recognize Moses. I've seen your question in the chat, and I'll ask it after Andrew asks this question.
Okay, thank you very much for this insightful discussion. And, Dr. Johnston, you talked about protocol, you talked about the things that South Africa, especially KZN, the things that we have seen coming our way. And I'm sure you've been part of the group, or say, people that have been advising the government on what's coming our way. Not only in KZN, the whole of South Africa is now getting involved in these thunderstorms, and the whole world actually. So what is your impression? Has somebody in the government or in the environmental department or, in the government ever heard what you say, or what advices have you scientists been given? What is it that, that catches up unaware like this?
Thank you for that. And hopefully we all, each of us as climate scientists, know a small part to make people aware of what's going on. The problem, I think, is complicated. Let's just look at the facts again. We are probably in the list of countries around about the middle, the 80th or the 60th most developed country in the world. So we're not up in the top 10 or 20 when it comes to developing countries with a lot of political weight and a lot of money to spend, but we are the 13th highest emitter of carbon dioxide on the planet. And in fact, Sasol 2 has got the single most concentrated production of carbon dioxide in the world. So we are players when it comes to contributors towards this. But you must also understand that the carbon dioxide that's produced at Sasolburg isn't causing the rainfall in KZN. There's not a direct connection between the activities of the South African nation and the change of climate. It's a combined thing. The atmosphere is connected. No one owns one particular part of the atmosphere. It's all connected in the processes that are happening around the world. And this is why we need global action. One of the questions that came up is about the COPs, and I'm not going to answer that in detail because you're going to have a speaker who knows a lot more about that. But our government, as well as other governments, have tacitly, which means they say that they agree with the general notion that we must reduce greenhouse gases. But when it comes to a socio-economic outlook, our Minister of Energy and Resources is saying, no, I'm sorry, we've got coal, we must use it. The other countries all used their coal when they had it, and now we must now not use our coal. Now that, to us scientists, is very short-sighted, but that's probably because we're so immersed in our science that we miss a little bit of the socio-economics. And I've spoken to coal miners in Mpumalanga, and said, and this is a bad thing, this climate change, and it's caused by the very thing that is your livelihood. And they say, well, what are we going to do? And I'm saying, well, you have to be helped. You have to be assisted. It has to be a just transition. We have to look at ways of introducing new skills to coal miners so that they can maybe install solar panels, repair solar panels, work on other sustainable energy infrastructure. So that's quite complicated. When it comes to governments around the world, you must understand that they are motivated by only one thing, and that's the election in 4 or 5 years' time. So very often we see commitments by one government which are then overturned by the next government, as you've seen in the United States and Australia. And that's very, very sad. I think that the fact that COPs have become more, we all know what a COP is now. Well, most people will know what IPCC is, and they know, and yes, that kind of awareness is helping. But we do need to still keep putting pressure on our governments. The scientists can advise as much as we like. The government is only going to act if the people are motivated, and if there are enough protests, there are enough people saying we mustn't do this and we must do that. And we've seen, because I live in Cape Town where Parliament is, the whole anti-nuclear thing, even though I'm not 100% sure that nuclear isn't better than coal, we've managed to stop the building of a nuclear power station for various reasons through protest. We're not sure what's going to happen to the car power ships, which are an environmental disaster waiting to happen. But people need to, I'm not saying rise up and revolt, please, I'm not saying that at all. They need to contribute on local, provincial and national fora to express their concerns so that the government does become more aware. But South Africa's got excellent climate legislation. It's got excellent policies. I've been involved in them, and there are many, many policies that exist. They're updated, provincial, local, and the municipality level. They're all there. But whether or not they're going to be acted upon in the long run remains to be seen.
Thank you very much, Dr. Johnston.
And thank you for your question, Andrew. And now we have Moses' question from the chat. He says, thanks, Doctor, for the informative presentation. You mentioned no action or commitment from COP so far. In your view, what are the reasons for lack of commitment toward proper mitigations and or readiness or adaptation?
I did try and answer that question in the last one, and I think it's the fact that the governments, they're looking around and saying, well, if you're not going to do it, I'm not going to do it. And so it takes leadership, and we're not seeing much leadership. And then, of course, we get things like COVID and war in the Ukraine, and it kind of deflects what's happening. But as soon as we get a natural disaster, people throw their hands up in the air and say, oh, we should be doing something. But then it's too late. So it's a case of, and I was listening to an interview yesterday, it's going to cost us much less to prepare for climate change and to try and prevent climate change than it's going to cost us to deal with it. But of course, we don't see that because it's money in our pockets now that we spend at the expense of something else.
Thank you. And we have another question from Hannah de Villiers in the chat. She says, thank you. Do you think livestock agriculture in South Africa will need to change to help mitigate further climate change, especially given the latest IPCC recommendations or a directive around short-term methane reductions? How realistic do you think this kind of change is locally?
So that's also a very good question, because our contribution from livestock to our methane or the carbon dioxide greenhouse gases in South Africa is very low. It's less than 10%. And that's because we don't have the huge amounts of cattle that we see in North America and South America. But having said that, the demand for meat is growing amongst the, when I say the demand for meat, the need for protein is growing amongst the less fortunate population, and they can't really afford meat. So in some ways, that's the good thing that we're focusing more on chicken and pork, for example, which are cheaper meats because they have less of an impact. But when it does come to livestock, people all like to eat meat. I don't say all, I'm saying generally people like to eat meat, and they see eating meat as a bit of a status thing. What I'd suggest is that we mustn't turn around and say, okay, we must have no more meat and no more cattle, because cattle are, in fact, an integral part of the savanna's landscape, of the natural vegetation. There's a symbiosis that exists. And I'm not saying we should kill those cattle and eat them. You know, they can peacefully coexist, or we can have wild animals there. But let's just say that a sustainable livestock industry is not going to be hugely harmful to the South African environment, and the contribution to greenhouse gases, if it is sustainable, will be at a level that is not alarming or is not going to make a huge difference. What we do need to incorporate is a reduction in the amount of meat we eat, for health reasons and for environmental reasons. So I don't say to people, give up meat, especially if I can't do that, but I do say to people, you need to cut out the amount of meat that you eat. And I quite happily will only eat meat twice a week, and it's not a hardship for me. But that's because I've got access to alternative resources. So it's a complicated question, Hannah. We can discuss it further. There are various organizations that talk about sustainable livestock management. There is free range versus a herd lot. There is different types of feed to reduce the amount of methane that cattle do produce. There are different breeds of cattle that might produce less methane that we can focus on. And I'll be at a large herds conference in June, and this point will be raised because it is becoming an issue. Thanks for your question.
Thank you. We have another question from Karabo Kiba. She says, why is it that when there's rainfall in the city, not all the areas receive rainfall? Can this be due to climate change, or can this be due to some geographical explanation?
Yeah, no, Karabo, this is a geographical distribution thing. In Cape Town, I've got a map that shows you the amount of rainfall that falls in Cape Town, and between Kirstenbosch, which gets 1,700 millimeters a year, and the airport, which gets 580 millimeters a year, is less than 10 kilometers. So there are all sorts of geographical factors that contribute. In Cape Town, it's mostly the mountain. In Gauteng, it's difficult to explain, but there are also topographical factors there. But there certainly are areas that receive more hail traditionally than other areas, and areas that receive higher rainfall. Generally speaking, we see more rainfall on the east coast because of the warmer ocean there, and less rainfall on the west coast because of the cold ocean. But it's a very big scale thing. We can get averages for certain areas, but within those areas, the variation is very high. So I'd put that under natural variation. But it's the nature of the rainfall that we're going to see changing due to climate change. It's the number of extreme events. It's the number, things like flooding and droughts and extreme intense rainfall. We may see the same amount of rainfall, but we see it falling in a shorter time. But to answer your question directly, it's more to do with the local variation than anything else.
Thank you for your question, Karabo, and thank you for answering. I also learned something here. And lastly, in the chat, we have Hannelene's question. I hope I pronounced your name correctly. It says, wouldn't it be beneficial to give government support to farmers that start to implement regenerative agriculture, as these practices, for example, improve water infiltration, carbon sequestration, and lower soil temperature?
Thanks, Annelien. Brilliant question. And if you haven't heard of regenerative agriculture, please Google it. I've got friends that are involved in that, and I've also given talks to their conferences and workshops. It's very, very important that agriculture starts looking holistically at the way they practice agriculture. They need to focus on the soil. They need to focus on water. Traditionally, agriculture just uses the soil as a medium. You throw fertilizer in it, you throw water at it, and you get a crop which is merely produced from the fertilizer and the water. What we need to do is to get integrated and work on sustainable agriculture, and the word regenerative means restoring the soil to the future levels, reducing the amount of chemicals, reducing the amount of water that we waste, reducing the amount of carbon loss. All these things are fantastic. Now, the point that Anneline's making isn't it, why doesn't the government support this? Because it helps everyone in the long run. Well, unfortunately, this country has a very, and all countries, in fact, not just this country, has a history where agriculture forms a very important voting bloc and a very important lobbying group in the government. And if you upset the farmers, you can really upset the nation. So by encouraging or subsidizing one farmer without subsidizing another farmer, you are treading very dangerous ground. Now, theoretically, if one could show that a farmer is practicing regenerative agriculture by having someone monitor what they're doing and testing their soil and testing their water, that would be easy to subsidize them. But because we don't really have that capability and that capacity, and the fact that chemical companies very much control agriculture in South Africa still, it's very, very hard. But there are very active groups doing regenerative agriculture that I've been involved in and I've seen happen, and they survive much more when the climate gets extreme, and they also reduce their input costs, which is what farming is all about. So it might just be that there's a natural selection that takes place, and those farmers who are doing regenerative agriculture become an advertisement for the practice that other farmers copy. We've seen that with the wheat growing regions in the Western Cape. All the farmers now practice some form of reduced till and some form of conservation agriculture in the Western Cape, because we know that they can't survive unless they do that.
Thank you, Doctor, for such an informative and interesting talk. And as Cheryl Ogilvie said in the chat, I think this presentation does need to be repeated within the Unlocking Nature series as well. I think it's something that still needs to be discussed in greater detail, because there's so much skepticism around climate change. Because, as you said, there's fake news running around, or the lack of actual evidence or scientific knowledge being used when climate change is being discussed. But yeah, I just want to thank you so much for this talk and for your time. And I just want to acknowledge the students from Free State University of the Free State and from Botswana International University. And thank you all for coming through, and all of you who are still here in the room. Thank you so much for joining us. And just a reminder for our next talk on the 4th of May, please join us. It'll be at the same time at 1 p.m. And we'll be looking forward to welcoming you then. So please join us. And thank you so much for coming. And thank you, Dr. Peter Johnston, for your wonderful talk.